Now we talk about the consistency or inconsistency of a system of linear equation. So first of all, we must try to convert a given system of linear equation to matrix form, and after converting it to matrix form, we'll talk about its consistency. How we can find whether the system of linear equation is consistent or not. See, if I am given only 3 linear equation or sometimes 2, we are here in class 12 we are going to discuss the 2 linear equations with 2 variables or 3 linear equations with 3 variables. Well, so if I am given a system of linear equation which consists 3 variables and 3 linear equation, so 3 by 3 variables and 3 equation will give us a 3 by 3 coefficient matrix, that is a square matrix, which is invertible or not. The solution will depend on that. Well, so here we have a1x plus b1y plus c1z is equal to d1. The second equation is a2x plus b2y plus c2d plus c2z plus d is equal to d2, and a3x plus b3y plus c3z is equal to d3. Well, this system of linear equation can be represented in a matrix. How? Simply what we do is we make a coefficient matrix, that is coefficient of x, y, z with sign. In the first equations are written here, and in the second a2, b2, c2 will be written in the second row, and in the third row we'll write the coefficient of x, y, z in the third equation in third row. Now we make the column matrix of variable, first variable, second variable, third variable, and in the right hand side we have the constants, the column matrix of constants on right hand side. Actually, if we multiply these two, if its order is 3 by 3 and its order is 3 by 1, so when we multiply we will get the order 3 by 1. Actually what we are going to get is, if I multiply a1x plus b1y plus c1z, a1x plus b1y plus c1z. Now the first is multiplied by first, now the second row is multiplied by this column, so a2x plus b2y plus c2z. Again a3x plus b3y plus c3z is equal to this d1, d2, d3. Now this is a 1 by 1 matrix, 3 by 1 matrix, and this is also 3 by 1 matrix, and these two matrices are equal, so obviously the corresponding elements will be equal. So a1x plus b1y plus c1z, a1x plus b1y plus c1z is equal to d1, this is equal to d2, and this is equal to d3. So this can be written as this, and this can be written as this. So basically what we do is, we just after this we write this. How? Here we write the coefficients of the 3 equations in first row, second row, and third row respectively. We write the 3 or 2, whatever number of variables present in the equation in a column, and the right hand side, the coefficient constants on the right hand sides. Right? Now this matrix is generally named with capital A. So this is A, and the variable matrix is named as capital X is equal to the constant matrix is given as capital B. Now to find the solution of this system of linear equation, what we do is we pre-multiply both the sides. We need to find the value of x, the variables. What we do, we need to remove a. For that what we do, pre-multiply both the sides by a inverse. So we pre-multiply both the sides by a inverse. Mind it, we cannot post multiply because post multiply is of no use. This is not commutative, so we cannot change the order, so it cannot be further solved. So you cannot write BA inverse. It is compulsorily you are going to write x is equal to A inverse B. That's why I am discussing it here. So what we do is pre-multiply. When we pre-multiply both the sides with A inverse, this is A inverse, right? A inverse into x, A inverse into B. A inverse into A is I. A inverse into A is always unit matrix. Unit matrix into x is x. So this is how we get x is equal to A inverse B, and x is equal to A inverse is 1 upon determinant A into adjoint A. Now we find, first of all what we do is we find adjoint A into B. Now let's talk about this. See, if determinant A is non-zero, then obviously we are going to get a unique solution. Determinant A is not equal to 0 means inverse exists. That means inverse is unique, so there will be a unique solution. Now we must discuss with the help of this. This is adjoint A into B upon determinant of A. Let's talk about this. If determinant A is non-zero, first of all we find the value of determinant A, that is the determinant of coefficient matrix. As soon as we find the determinant of A, if determinant A is non-zero, that means we can find its inverse, that is a unique solution exists. And in most of the question of exercise 4.6, what we are to do, we are to find the solution of system of linear equation. We are to find the solution, means solution exists, we are to find only. So in each and every case, question number 7 onward, we will be having determinant A is non-zero. But in the first 6 question of exercise 4.6, we are to check whether the system is consistent or not. Consistent means the solution exists. If the solution of given system exists, means if there is such value of x, y, z which satisfy all the given equations simultaneously, then the system is said to be consistent. And if there is no solution of that system of linear equation, then it is inconsistent. Consistent means the solution exists, whether there is a unique solution or infinite many solution. Inconsistent means the solution does not exist. Let's talk about this. See, if determinant A is non-zero, then without any doubt there will be a solution, and that solution will be unique, so the system is consistent. So in exercise 4.6, in most of the question we are having determinant A is not equal to 0, so we will write the comment, since determinant A is not equal to 0, so the given system of linear equation has a unique solution and the system is consistent. If it has solution, that means it is consistent. Now let's talk about, if determinant A is 0, then what we do, we find whether it is taking 0 by 0 form or what. That is, we find the value of adjoint A into B. We find the value of adjoint A into B. Okay, how we do it? We find the adjoint A into B. Adjoint A is a matrix and B is a matrix. The product of these two matrices will be a matrix. If this matrix is a zero matrix, if this matrix is a zero matrix, then the system is inconsistent. That means if determinant A is 0, but this is not equal to 0, that means this quantity is not defined, that means solution cannot be found, the system is inconsistent. This is surely, whenever adjoint A into B is not equal to 0, that means the system is inconsistent. For determinant A is equal to 0, inverse exists and a unique solution exists, that means the system is consistent. If determinant A is 0, then we find adjoint A into B. If adjoint A into B is equal to a non-zero matrix, then the system is inconsistent. But here is an important point, that is most important, because in some of the books it is not clearly given. There is a mistake in some of the books. See how. If adjoint A into B is equal to 0, then the system may or may not be. There may be solution 0 by 0 form. You must have heard it in limits and continuity, 0 by 0 form. We can find sometimes the limits can be evaluated and sometimes limit does not exist. See here, it may or may not be consistent. And how we check? We try, either you learn the Parmar rule or in the previous classes we have studied elimination of variable and by other methods we can find the solution. I'll discuss this part particularly. Let's have an example. Well, here we first discuss the questions 1 to 6 of exercise 4.6. Those are very simple questions. See, whenever we are to find the consistency of the system of linear equation, what we do? Very simple. First of all, we write the given system in the form Ax is equal to B, and then we find the value of determinant of A. Well, whenever determinant A is not equal to 0, that means inverse exists and unique inverse exists, so a unique solution exists, that means the system is consistent. So question number 1, question number 4, question number 6, for these questions of exercise 4.6, determinant A is not equal to 0, so unique solution exists, that means the system is consistent. Well, in question number 2, 3 and 5, determinant A is going to be 0. When determinant A is going to be 0, then we find adjoint A into B. We find adjoint A into B. B is the coefficient matrix, which are the right hand side constant matrix. So adjoint A into B, if the value of adjoint A into B is 0, not equal to 0, and in all the cases, question number 2, 3, 4, 5, in the remaining cases, adjoint A into B is not equal to 0. So these systems are having no solution. The solution does not exist. That means the system is inconsistent. So 3 equations are consistent and 3 equations are inconsistent. But this is the most important point which we are to discuss. Well, if determinant A is not equal to 0, alright, in question 1, 4, 6, the system is consistent, the solution exists. Determinant A is 0, then there may be 2 cases. We find adjoint A into B. If it is non-zero, that is in question number 2, 3, 5, that means the solution does not exist. Solution exists, solution does not exist. But here, this is the most important point which is not discussed in our textbook. Let's try to discuss it. If adjoint A into B is equal to 0, then system may or may not be consistent. Mind it, it's not consistent. It may be consistent or may not be consistent. Let's try to take an example with the help of geometry. Let's see it. Well, we have the equation of line x plus y is equal to 3. If I multiply both the sides, I get this equation. Means these are the equation overlap lines. That means each and every point on one line will exist on this line also. That means it will have infinite many solution. We know it already. So how we proceed? We write it in the matrix form. Ax is equal to b, coefficients 1, 1, 2, 2, 1, 1, 2, 2. The variables x, y in a column and the right hand side constants 3, 6. Here the determinant A is 1 into 2 minus 2 into 1. Determinant A is 0. If the determinant A is 0, then we find adjoint A into B. Now how the adjoint A is found? For adjoint A of 2, for a adjoint of 2 by 2 matrix, what we do? We interchange these two and we change the sign of these two. So this 2, 1, 2, 1, and changing the sign minus 2, minus 1, minus 2, minus 1. Adjoint A into B. B is this matrix 3, 6. Now this row will be multiplied by the column 2 into 3 plus this. This will give me 6 minus 6 is 0. Again this row is multiplied by this column minus 6 plus 6 minus 6 plus 6 will be 0. So adjoint A into B is 0. Now adjoint A into B is 0 means may have infinite many solution or may not be. Now this is the part where we are having infinite many solution, which we already know. See how we proceed. We take any arbitrary value of x. We take x is equal to k, where k is any arbitrary real number. So I put x is equal to k and find the value of y. Y is equal to 3 minus k. If I put y is equal to 3 minus k in this equation, in the left hand side, I find that left hand side is always equal to right hand side. Means if I take x is equal to k, then y, from equation 1 y is equal to 3 minus k. If I put x is equal to k and y is equal to 3 minus k in this equation, the left hand side is always equal to right hand side. See how the left hand side becomes 2 into k, x means k, plus 2 into y means 3 minus k. So 2k plus 6 minus 2k, 2k is cancelled out, 6, and that is right hand side. That means, so any point of the form x is equal to k and y is equal to 3 minus k will satisfy this equation simultaneously, both the equations simultaneously. So it will have infinite many solutions. So the system is consistent. This system is consistent. But on the other hand, we can see here determinant A is 0 and adjoint A into B is 0 and the system is consistent. But here determinant A is 0, adjoint A into B is 0, but the system is not consistent. See it carefully. We are having one equation. This is equation of plane in 3-dimensional geometry that we'll talk in 3D geometry in class 12, last chapters. Well, right now, actually what I have taken one equation. I have multiplied both the sides by 2, but here what I have done, I have multiplied the left hand side by 3, but I have changed the right hand side. So these are not, the first two planes are showing the same plane, but the third one is a parallel plane. So these two planes are having common solution, but the third plane is not having any common point with the first two, so it will have no solution at all. Okay. So what we'll do, first of all we find determinant A. Determinant A obviously 1, 1, 1, 2, 2, 2, 3, 3, 3. If I take 3 common from here in the determinant, I will get same. So it will be 0. So determinant A is 0. Now adjoint A. Every minor is 0. 6 minus 6. If I try to find this minor 6 minus 6 or this minor 2 minus 2, so all the minors are 0, so the cofactors are 0, so the adjoint A is transpose of cofactor matrix, so adjoint A is a 0 matrix. Now if I multiply adjoint A with B, this is adjoint A which we have found, and B is 1 to 4, 1 to 4, and obviously 0 into 1 plus 0 into 2 plus 0 into 4 is 0, 0 into 1 plus 0 into 2 plus 0 into 4 is 0, again 0, that is a 0 matrix. Here adjoint A into B is 0, but the system has no solution. Why? Because this will not have any common solution. See, if I take x plus y plus z, x plus y plus z is equal to 1. If I put this in equation 3, what I find? 3 is common. X plus y plus z is equal to 4. 3 into 1 is equal to 4. 3 is equal to 4, which is absurd. It can never be, 3 can never be equal to 4. That means this will not have any solution. So you can observe, if adjoint A into B is equal to 0, then it is needed not to be consistent. The equation may be consistent, the system may be consistent, or may be inconsistent, as the case may be. That is what we can discuss about consistency. Let me again tell you the process. What we do? Actually, the solution is x is equal to A inverse B. That gives us 1 upon determinant A times of adjoint A, right, into B. So we find determinant A. If determinant A is not equal to 0, that means unique solution is there. But if determinant A is 0, then we find the numerator, that is adjoint A into B. If adjoint A into B is not equal to 0, then there is no solution. If adjoint A into B is equal to 0, then solution may exist or may not. But even in our textbook, only those cases are given. Whenever determinant A is 0, only those cases are given where adjoint A into B are non-zero. So adjoint A into B is a non-zero matrix, so the system is inconsistent, the solution does not exist. But here, when adjoint A into B is equal to 0, adjoint A into B is equal to 0, here the system is consistent, and here the system is inconsistent. Here the solutions exist and infinite many solutions are there, but here the solution does not exist. That means this system is inconsistent. So on adjoint A into B is equal to 0, the system may consistent or may not be. That's all about it.